It was the countdown to my Screencastify because it's recording my screen for Matt. My problem is I don't know how to get the sound to work. Oops. I got the sound to work as in it records sound, but it records it very, very quietly because it's using the mic on my desk on my laptop. Yep, you're going to need your desktop at some point, so I don't know if you just want to open up everything on your desktop to start with or what you want to do. Ew, none.
You would not eat that for $1 million.
I get down eating that. The X-Man phone's like pops.
I don't know if you get that.
Good.
Okay, well, we have so much to do today, but let's take a moment to read the warning label here.
The warning label? Oh. Or you could not consume.
First aid. Oh, it's got first aid on it.
Nice.
Sorry, I didn't see that there.
Ingestion. Give fluids, do not induce vomiting. It just says drink lots. Avoid inhalation, skin contact, eye contact may cause sensitization.
Eye contact. You're making eye contact with it right now.
Now, I don't know what that means.
It's all
Oh, it's all.
digestive system.
Yeah, would you eat it for
Oh, what if it expands in your stomach?
Would you, how much would you eat it for, honestly?
No, what if it expands in your stomach?
Like, see that right there. How much would you eat? Honestly.
First of all, I gotta know what happens if I do eat.
Oh, without knowing, you can't know what happens.
I'm not taking that risk.
Okay, we're going to go ahead and get started. So again, you may want to log into your laptop or desktop when we to start today. Yesterday we talked about fault tolerances. Today we're going to start with a video about fault tolerances, and as you can see in the top corner, we have a different teacher today. I'm not sure if we've had this teacher yet before.
It's different for me.
So we'll see. We'll see how this goes.
Hello, and welcome to today's AP Daily video about fault tolerance. My name is Mrs. Julia Lano, and I teach at Hamilton Southeastern High School in Fishers, Indiana. In this video, we'll look at different network solutions that are fault tolerant and how that facilitates the transfer of data. So what exactly will we learn? What are our essential knowledge statements? We're going to be talking about the internet again and explain how a given system is fault tolerant, so like the internet. Here are our essential knowledge statements, again, including redundancy and how to accomplish a fault tolerant network. Let's take a look at an example. So here's a similar example that we saw in the previous fault tolerance video with the network that is fault tolerant. But how does fault tolerance make this a good network? So in taking a look at this network, there are multiple paths that data can travel to get from one device to another. Those multiple paths make the network fault tolerant. That also makes the network even able to scale. So let's take a look at what if we add more devices to our network. What does the additions do to our network? So here you see we've added H and J and a connection from H and J to the rest of our network. And they each have two connections. So again, each one of our devices has multiple paths to every other device on the network. So with more devices and more network connections, it only makes the network stronger. So we are able to continue to add devices and connections to the internet that we know today, and it continues to grow and stronger and is able to scale, and we continue to use it without any issues. Although they do happen, but it is fault tolerant, and so we are all able to do things like record this video and watch videos online. So let's practice some questions. Which of the following is not a benefit of a fault-tolerant network? A, data has more than one path to travel from one device to another. B, if part of the network fails, the network can still function by using other paths. C, data will only take one route from one device to another, no matter the number of routes available. Or D, more devices creates more connections and makes the network stronger. So hopefully you were able to determine, as we just talked about, how more devices make a network stronger, and we've talked about multiple paths making it redundant and fault tolerant. So the answer here is C. Data will only take one route. That is not the case. We've talked about how data travels along many different routes and takes the most efficient route at the time, or the fastest, less trafficked, or the one that's not down. So it can take any of the routes at once. So one route is not the option. Try another one. What would make this network fault tolerant? A, add a connection from A to B. B, add a connection from B to C. C, a connection from E to G. Or D, a connection from E to F. So again, we want to...
Yeah, this one you have to think about. Every computer on that network, every device on that network needs to have two ways of getting out.
So A and B. Wait. Because what? G has, it can go to either B or H, H can go to either F or G, A can only go to F. So that one would be at least like all these other ones have two paths. You see that? Five things again.
I'm going to take a look at, are there paths going from each of the devices to each of the other devices, or is there only one? So it's pretty quick and easy to look at the devices and see how many paths are leaving that device, or how many paths are going into that device. And you can see most of our devices have 2 or even 3 paths, except for device A. There's only one path from device A. So that leads me to my answer, which is A. I need a connection from A to B, and that will make this network fault tolerant. Now, more connections can always make the network better, but again, that does take resources. So fault tolerance is just to make sure we have at least more than one path from each device. So what should we take away from today's lesson? That our fault tolerant system, the internet, is a very good system based on the redundancy and the multiple paths that data can travel, which makes the network only stronger and able to scale, which is why the internet keeps growing the way it does. Thank you. Have a great day.
That's it for that one. Yep, for sure. Okay, we're gonna pop into your textbook real quick.
Hello, and welcome to today's AP Daily Video.
In your textbook, we are going to start. No, not there. Right here, measuring latency. So 223 going to measuring latency. Now yesterday we played with IP addresses. We used our computers to look up some IP addresses. Today we're going to look at what's a term called latency, which is one of your vocab words. So either one of you want to hazard a guess as to what it means.
Latency is like how long it takes.
The measure of the delay in communication between the two devices. Okay? So that length of time in between getting things to those two devices. One machine repeatedly sends packets to another asking for a response or an echo, and the target machine responds. Once it's complete, it reports how long each round trip took and whether any packets were dropped. So we're going to be using what's called the ping command, P-I-N-G, and the ping command. So in your VS Code, so you're opening up Visual Studio, so you're going to have to log into your desktop there. Once you're in Visual Studio Code, you're going to make sure that terminal is at the bottom of your screen. If it's not, you're going to go to View Terminal so we can have that prompt at the bottom. If you've got that prompt, we're going to ping And I apologize, I'm teaching from back here so that my voice can be picked up from the laptop for a Mac. You're going to ping your favorite website or any website. So you're going to type in ping, P-I-N-G space, www dot whatever domain name you want to ping. That's school appropriate. So you can even ping the school's website for that matter. mbsd.net. Yep. It might take a little bit. Okay, so every time it says request timed out, it means it's sending a message to the school's website and the school's website is not responding. Yes.
Sent 4, received 0, lost 4, 100%.
There you go. So 4 packets are floating out there in cyberspace, never to be returned again. Go ahead and give it a try, Eli. Try that again, or pick a different website.
I expected that.
We use YouTube.
There you go. So what should happen, and if you look up on the board, they have the example that they did a ping for the pltw.org website. What should happen is it should list the IP address that you get the reply from, how many bytes were sent, how long it took. MS stands for millisecond. MS stands for millisecond.
43 milliseconds.
So in most cases, it didn't take very long, right? It was there and back. It also tells us how many packets were sent, how many were received, lost, round trip in milliseconds. Did we get something this time?
Yeah.
Awesome. Questions on IP addresses, communicating, things like that. Okay, the next thing we're going to look at is what's called data compression. And data compression is when we're sending data across the internet. A lot of times things get lost or things get changed around. Okay, so we're going to talk a little bit about data compression. I think we've seen this teacher before. She's pretty good, pretty on task here. But we're gonna watch this video. This one's about an 11-minute runtime, and she's gonna talk about data compression. Then we'll review.
Hello, my name is Angelina Dominguez, and I teach AP Computer Science Principles at Veterans Tribute Career Technical Academy in Las Vegas, Nevada. I'm excited to be talking today about data compression. So let's look real quick about what we're going to learn. So we'll talk about data compression algorithms, specifically what it is and how it reduces the size of data. We'll compare different types of data compression algorithms. And finally, talk about situations in which you would use the different compression algorithms. So let's get started. Data compression is a reduction in the number of bits to represent data. We do this to save time and to save space. Storage capacity and network bandwidth always has limitations, so compressing data can save storage capacity, speed up file transfer, and even decrease costs for storage hardware and network bandwidth. Remember, every bit of data or information can be stored digitally, whether it's text, pictures, music, or video. All of it can be represented digitally, which means the information is represented on a computer by ones and zeros or on and off electrical signals. But representing information digitally can take up a lot of space. For example, let's say we wanted to store a 3-minute song. Well, that could take around 30 megabytes of space. And a 1 hour video could take like 800 gigabytes. So what happens is that digital information is compressed to take up less space. That 3 minute song could be compressed down to, say, like 3 megabytes. And that 1 hour long video could be compressed to be 1 gigabyte. When data is compressed, you're essentially looking for repeated patterns and predictability, redundancy in the data. So for example, let's say we have some X's and O's like this. We could compress this to be X3O2 X2. Now, this might not seem like it shortened the information by much, which is true. But the larger the data file, the more patterns that can be pulled out from it. Text compression can be as simple as removing all unneeded characters and inserting a single character or even a symbol in its place, like this. If each letter is a byte of data and the original text contained 28 bytes, this was now reduced to 15 bytes of data, which means we just can compress this text by 46%. So let's look at some examples. So here's an example of a compressed piece of text, and here is the key to go along with that. So what I want you to do is pause the video and see if you can decompress this compressed text and recover the original. Unpause when you think you got it. Welcome back. Did you get Humpty Dumpty?
Sorry,
Awesome.
wasn't fast enough.
So the original text was 142 bytes of information. The compressed ended up being only 80 bytes. But we also have to send this dictionary or this key along with the compressed text in order to recover the original. And the dictionary was 31 bytes, 1 byte for each letter and 1 byte for each symbol. So that made our compression rate about 21%. Now, the thing to remember about compression is that there's no one right way to compress. There's many, many compression algorithms out there, and each one works a little bit differently to compress the data. Now, pictures are a little harder. Coming back to this idea that what makes things compressible are patterns and predictability and redundancy. If you think about a photograph, some photographs do have predictable areas. You can take a picture of a small desert island in the middle of the ocean with a couple palm trees like this, and this is a little bit easier because the sky is smooth and basically one color, giving you thousands of blue pixels. You have hundreds of yellow pixels for the island, a few hundred more for the trees. So you can compress it not by sending every single pixel individually, but by saying, there's the sky with the color blue, and there's 1,000 of those. Just replicate them. Pull out these individual pixels and replicate them. The computer knows how wide the picture is, so the computer can just start duplicating the blue pixels in the right XY positions. You don't have to say, here's the specifications for blue pixel at position 1000. And here's the same spec for the blue pixel at 1001. And here's the same spec for the pixel at 1002. You don't need to do that. You just send the spec once and say, replicate it 400 times. Both of the methods that I just explained would be considered lossless data compression, because the original data was compressed, or the original data that was compressed can be recovered without the loss of a single bit of data. In essence, the dictionary is sent along with the compressed data file at the other end. The compression can then be reversed or decompressed, and we can recover the exact original data. Lossy compression, on the other hand, is a type of data compression where data is thrown out and cannot be recovered. This might be done with music files. Well, for example, like music, there are sound frequencies that may be out of range for the human ear. So if we take those sound frequencies out that the average person can't hear and we throw them away, the file will be smaller and most people would never be able to tell. But imagine if we used lossy with a text file like this, and we had these words, food, fed, feed, feud, fed, and the compression algorithm threw out all the vowels. Well, we wouldn't really be able to tell the difference between these compressed words. So lossless data compression is the typical approach with executable files, as well as text and spreadsheet files, where the loss of numbers or words would change the information. Since lossy compression permanently eliminates bits of data that are redundant or unimportant or even imperceptible, lossy compression is used or is good to use with graphics, audio, video, and even images, where the removal of some bits of data has little or no discernible effect on the representation of context. A good example for lossy compression with images is the JPEG algorithm. You may have heard of the term JPEG before. It's a type of picture. It's many times necessary to get a photograph sized down in order to upload them and send them to somebody, or to upload them to an online storage site like Picasso or Flickr. Those sites are not going to be happy having every single one of your pictures taking up to like 20 megabytes and being utterly perfect. They want you to compress it down to kilobytes, as small as possible. Now, while there are some images out there that you could use lossless compression because they have patterns like that desert island in the ocean example, there are many other images out there that are just innately random looking enough that they are not easy to compress. So what the JPEG compression algorithm basically does is some really clever things which make many parts of your images end up looking a bit blurry or fuzzy if you were to magnify them. Now it does this by dividing the picture up into blocks and squares and saying, well, the sky here on this picture on the left is almost the same blue across. It's a little bit darker on the left and it gets lighter to the right. So I'll just use an approximation. It takes those three colors or the colors of the sky across the whole sky, and it makes an approximation, and that's now the sky color, just one solid color. So if we were to zoom in to a JPEG, you'd see what looks like to be a blurry pixelated image. It's never recoverable exactly the way we started, but you get more compression this way, if you don't mind an approximation. And for most people, the human eye can't really tell the difference. And we think we were looking at something that looks pretty nice. So which type of compression is better, you might be wondering? Well, it really depends on your needs, as there are trade-offs for both. Lossy data compression can significantly reduce the number of bits stored or transmitted, but the original data can't be recovered or restored. On the other hand, lossless data compression does let you restore and recover the original data, but lossless compression usually cannot compress data as much as lossy can. So, which do you choose? Well, in situations where quality or the ability to reconstruct the original data is important, you should choose the lossless compression algorithm. But if having the smallest data size or transmission time is what's most important, you should choose a lossy compression algorithm. Just remember that just because we're compressing data doesn't mean less information. In the case of lossless, we have a smaller data file, but the original can be recovered. And in the case of lossy compression, while there may be pieces of data that are thrown out to make a smaller data file, no actual information is lost as far as the human eye or the human ear can tell. So we reached the end. What did we learn today? So we looked at data compression, and we saw how fewer bits does not necessarily mean less information. We looked at how data compression can reduce size. We also compared two different types of data compression, the lossless and the lossy. And we also looked at situations in which you would use the lossless or the lossy compression. So that's it for today. I'll see you soon. Bye-bye.
Okay. So
Hello, my name is Angela.
data compression, and this is something that when you guys had to upload your files to AP Classroom for your create task, that you kind of looked at data compression because you had to compress, some of you had to compress your videos. So data compression is useful when we're transferring data between devices, networks, when we're moving things around. What is the difference, and she just talked about this, what is the difference between lossless and lossy?
It's like when you're at so the certain words, like she was using like feud, food, I mean feed, bad, those kind of words. Like if you're just using the FD, it won't help you, so you have to like make it like different like words, like letters, for example, words.
So what kind of compression was it called when she was using those words? And then the vowels all disappeared. Was that lossless or
Lossy.
lossy? Lossy, right? Because we lost some of the data along the way. Absolutely. And then lossless is when everything comes out exactly how it sounds. So when we're looking at text compression, one compression algorithm takes advantage of repeated numbers, for example, and then they show you how they've compressed some of the numbers here. The problem with you compressing numbers is that sometimes you have to send a key along, and they showed us like the Humpty Dumpty thing, where they can send a key with decompression. When we talk about uncompressing, we're talking about making things back the way they were. Okay. So they have an example of Peter Piper picked a peck of pickled peppers. I don't do tongue twisters very well. But this poem has a lot of redundancy, right? There's a lot of repeating in this one. So this is one of those things that we can compress. Text is sometimes tough to compress. But you have, for example, and they pointed out like the ER repeats a lot. It repeats in Peter and Piper. The CK repeats a lot in picked and peck of pickled peppers. So there's things that we can compress in this tongue twister in order to make it easier to send. Questions on lossy, lossless? Okay, so the next thing we're going to talk about is media compression. We're going to talk a little bit about metadata. We said metadata was information that we can't see. It's information that's attached to our files, like the time and the date and the file type and things like that are attached that we just can't see. It's metadata. Okay. So your image files contains metadata about each pixel in the image. I thought the picture that she had of the two islands, when I first looked at them, I thought they were identical. I didn't even notice that the one on the left had a lighter color in the sky. And then when she started talking about it, I was like, oh yeah, I guess that picture is different. So that kind of shows that, when you're moving those pictures around, moving those videos around, losing a couple pixels here and there isn't going to be the end of the world. The bigger the image, the bigger the file size, because the number of pixels is larger, requires more metadata to be stored. The richer in color, the bigger the file size to store that wide variety of color. And the higher quality, the larger file size. So some things that when you're moving pictures and video around, things you want to think about when you're creating those files. The next section, they were having us open files in different formats just to show that they're different. They're saved in different megabytes, but I'm going to skip through that one. Videos are the same way. The smaller files are great. They call it fidelity, the extent to which the copy is identical to the original. Smaller file sizes are great. That usually means lower quality in your video. So it depends on what you're using the video for. Right? If you're sending somebody a video just for fun or uploading a video that doesn't really matter, that's one thing. If you're sending videos like to AP Classroom or to your professors in college or something like that, that might be a different situation. Or if you're putting them, when the news stations are putting things on air,
Yeah.
they're not going to use smaller video sizes. Questions? Okay. In your Google Classrooms, actually, nope, I lied. In your AP classrooms, we're going to the wrong classroom. Now this, if I remember correctly, well, before you get on there, hold that thought. If I remember correctly, this quiz for this week, it says April 12th, the right one. I had an issue. So you're going to have two. We're only doing this one that says the right one. Unfortunately, it put it in a lockdown browser because some of the questions I picked were from the practice exam, which is important. You wouldn't know. But it put it in a lockdown browser. So if I remember correctly, you have to log out of your Chromebooks to get to the lockdown browser. We did these before. I know we did one before. So I feel like you had to log out of your Chromebooks. And then there was something. Apps. Can you go to apps on the left? College Board. There you go. So on the left, there's an apps button. Once you've logged out of your Chromebook, on the left, there's an apps button, and then there should be a College Board button. And then it brings you to a College Board login screen. So go ahead and log in. Did you even log in?
No.
I didn't think so.
Yeah, I don't know what that means. Just
Hopefully you remember your logins because it doesn't save it when you log out of your Chromebook.
yeah.
You might have to log back in to get them and then log back out.
That was your username. Well, I thought it was a name.
I think it was whatever you wanted it to be. You may have to log back into your Chromebooks and get your login info. Oh, maybe not. Maybe.
Yeah. Well, it's just the first letter of your first name or your last name. That's my username. Then your password, you have to know.
Top right, it says AP Classroom. No, it's all the way to the right. Okay, maybe that one might work too. There you go, this one right here, the week of April 12th, right now. And you guys can work together. I had it not shuffle the questions on purpose so you can talk to each other through them. If you want to give it a try on your own, this one's longer. It has
30 questions.
Yeah, this one has 30 questions. You have whatever time's left today, class tomorrow, and then whatever you don't finish, you have to do for homework.
So we have time tomorrow?
Yes. Yes, you have all class tomorrow to work on this. Okay, so again, Matt, you're going to have to log out of your Chromebook and go to apps and click on College Board. Log back into your College Board account. Click on AP Classroom, and the test is called Week of April 12th, Right One. Okay, there's two different tests that say April 12th. Make sure you grab the one that says the right one. And that needs to be done by Monday, if possible. Should be by Monday because there's only 30 questions. Have a great day.